Hello and welcome to this lecture 3 on machine learning. In this lecture, we will more formally talk about linear regression and the least square fit to linear regression and different variants of the same. So we will present some formal definition, setup notations that will help us appreciate linear regression more generally. We'll also consider variants of linear regression, and finally we'll present a least square solution to the linear regression problem and present a geometric interpretation to the same. Now for us, linear regression is only a canonical example that also helps us appreciate many other aspects required for machine learning. For example, optimization. We'll see how we can formally derive the least square solution to linear regression. A very important topic, which is overcoming the overfitting problem, and toward that we'll present a probabilistic interpretation to linear regression and then a Bayesian estimation for the parameters of probabilistic linear regression. That will also lead us to the more general concept of regularization. We will also discuss nonlinearity that can be attained through different formulation of linear regression. This could be variants both in terms of the error function and also through the regularizer. That will lead us to the topic of kernels, which are basically tools for getting high dimensional embeddings for example inputs, but obtained implicitly through dot products. So more about this later. Finally, we'll discuss non-parametric estimation and also highlight what has been parametric about our estimation so far. So an illustration, imagine that you have some independent variable such as investment into a TV commercial. So you're running a company and you want to know how much to invest into a TV commercial. And what is the output or the dependent variable? It is basically the sales. So is it that higher the investment, more the sales? A company really wants to determine how much to invest based on a desired output level that it targets. So Y star is the desired output level. Please note that we are still trying to predict the dependent variable Y star based on the independent variable, which is X, or the investment into TV commercial. Just that we have presented the problem as slight different flavor, which is we're trying to find the right amount of investment to get a desired level. So our investment still will remain the input variable. But what is the basis for learning such a function f and determining Y star based on X, and also reverse engineering and finding the X to get a desired Y star? The basis is previous observations of the form xi yi. Xi is the instance of money spent on advertisements in the past, and yi was what was harvested as returns. Now, linear regression model, we make an assumption that y is a linear function of x. And as I pointed out earlier, once we have learned y, or rather learned beta naught and beta 1, we could always go back and find x star for a desired y star. The problem of estimating beta naught and beta 1 is precisely the problem of estimation for regression. We'll deal with estimation for several supervised learning problems, regression being the simplest of them. However, when we plot xi's and observe the corresponding yi's, we find that treating the investment as a single value and trying to predict the sales based on that investment might not be a good idea. Especially, it doesn't lead to a very neat linear fit. As you can see here, the linear fit is here, but doesn't look very convincing. Why is it so? Well, we landed up treating our investment as a single number. What about treating the investment as an object? Now, the object could have multiple attributes. I'll call them or denote them by phi. So phi 1 xi could be the date of investment. phi 2 xi could be the value of investment. What I've tried to fit here is yi as a function of just phi 2 of xi, the value of investment. Perhaps I should consider fitting yi as a function of several such phi's. So what does this mean? We are trying to get a somewhat nonlinear function of the xi's, but a linear function of the phi's. So y equals w transpose phi x. Expanding it out, it will mean summation I equals 1 to n wi times phi ix. So weight wi assigned to the phi I, or rather the ith attribute. So my linear regression is linear in w's and linear in the phi, but non-linear or not necessarily linear in the x. And the non-linearity is courtesy the phi. So my phi is a vector, and so is my w. Just recap the example of phi's. So phi 1x could be the date of investment, phi 2 could be the value, phi 3x could be the time of investment, or rather the time of commercial. You could also look at the duration of commercial and so on. So possibly my y indeed turns out to be a linear function of x mapped in this somewhat non-linear space. I mean, it's linear in the phi's in the eventual space, but non-linear in the x. So continuing with this notation, the data set D will consist of m training examples x1 y1 to xm ym. The x's will be the input or independent variables, the y's will be the output or dependent target variables. We'll try and use j as an index into the training set. So xj yj is a specific training example. We'll try and use i's as indices into the attribute functions. We'll also call them basis functions. So the phi's could be very specifically designed for a domain, but there are also general classes of basis functions which could be obtained off the shelf. Examples are the radial basis function or the Fourier basis or wavelets and so on. And the general regression problem is to find a function f in some class or space of functions such that you minimize an error. Now the error is what will help us determine the best predictor. So if the prediction with respect to an f is very far from what we observe in the data set, you would incur higher error. One can get more specific and choose a particular class f which invokes parameters w. So for example, f, if it's chosen as a linear class or class of linear functions, will basically be all the w's such that w transpose phi x is fx, or rather w transpose phi x is what should be matched with the dependent observation y. A small note here, as far as linear regression is concerned, we might switch between the use of a bias in the linear function, and often we might even just drop that bias. So the most general setting, we have a linear function f phi x w as w transpose phi x plus b, and as I pointed out, we could drop the b How do we do that? Well, we can drop that b by expanding phi to phi tilde and w to w tilde. Now what is this phi tilde? Phi tilde is nothing but phi, but with a 1 padded at the bottom. W tilde is nothing but w with a 1 padded at the bottom. So please get comfortable with both the use of b and the dropping of b. So with this parameterization, the problem is to determine w star such that you minimize the w, the weight for the linear function. One might also use the b and do an argument over w and b. Now what should be the error function? The error function, or the function to be minimized, could be determined based on what is a good or a generalizable model. For example, we have already motivated the sum of squares error. Where the error function is a sum over all the data points of the desired dependent output yi, and from that you subtract w transpose phi x and square this. So this gives rise to the least square linear regression problem. Now you could consider variants of this where you make changes to the error function or the objective function. Ridge regression is an example where you introduce a shrinkage parameter. It's also called a regularization parameter. So you consider the least square function, but to that you add a component norm w square, the Euclidean norm of w squared, and this is added to reduce discrepancies due to variance. We'll present some very specific details of ridge regression in the following lectures. We'll also present a probabilistic motivation for the introduction of the norm w square. But suffices to say that this gives rise to another class of regression called ridge regression, and this gives you an additional advantage that the models generalize well beyond the training data. More about this later. One could also look at regression where the dependent yi is not necessarily real valued. For example, it could be binary 0 or 1, as is the case with classification. In logistic regression model, the function to be predicted is basically the log of the odds, the probability of y given x divided by 1 minus probability of y given x, the log of the odds. And this is assumed to be a linear function. So in some sense, this is still a linear regression problem, but there is a transformation that is performed on the space of predictions. So what you predict is not based on f directly, but based on the probability. We'll also discuss variants such as lasso regression, where you consider the error function as the least square error, but instead of a shrinkage using the Euclidean norm, you use the L1 norm. More about these later, but this was, I think, a sufficiently representative set of variants of linear regression, and we'll find that these variants also hold for other supervised learning problems.